Let us now discuss about the atomic model. First of all, what is an atomic model? The atomic model is something that tells you about the arrangement of fundamental particles. Model that tells about the arrangement of fundamental particles or the subatomic particles in an atom. You know that the fundamental particles are nothing but electron, proton, and neutron, right? Now, how are these electron, proton, and neutron arranged in an atom? Okay. First one to explain about the arrangement of fundamental particles in an atom was J.J. Thomson. In the form of Thomson's atomic model. Okay. You know, according to Thomson, atoms are spherical in shape. Let me just draw a sphere. Okay. Atoms are spherical in shape and you know the positive charge is thoroughly distributed throughout the atom. Let this be the positive charge. Okay. So this way, the positive charge is thoroughly distributed throughout the atom. I mean, it is uniformly distributed. Let me say that this is the positive charge, nothing but the proton. And you know, the electrons are embedded. Electrons are arranged. Let me just draw them this way. Okay. They are embedded in the positively charged sphere. This way. You can show some more. Okay. So simple three things. Let me just tell you that the atoms are spherical in shape. Point number one. Okay. Then the second point is positive charge. Is thoroughly distributed or say is uniformly distributed throughout the atom. And the last one. Electrons are embedded, I mean arranged in the positive charge of the atom. Okay. Now this particular model was given different names. Like for example, see, it appears to be a kind of plum. Plum, of course, we say regu pandu. It was given the name plum pudding. Pudding is in fact a kind of sweet. Okay, plum pudding, like a cake. Or raisin pudding. Raisins, I hope you know. Plum pudding model, raisin pudding model, or the more famous watermelon model. It is just like the watermelon, isn't it? It is just like the watermelon in which the positive charge is thoroughly distributed and the seeds are just like electrons which are embedded in the positive charge, right? So you can visualize it as a watermelon in which the red one, the material is thoroughly distributed, the positive charge in which the electrons are embedded. It is in fact like a watermelon, right? You know, the problem with this model is, you know, the protons and electrons are placed collectively. Of course, he explained that the positive charge is of course neutralized by the negative charge on the electron. Right. Of course, he could explain about the electrical neutrality of the atom. But the problem is, you know, the protons and electrons were placed collectively. Though it was okay, though it could explain many things about the atom, it failed to explain some experimental results. So this model was discarded. Okay. Later on, Rutherford and his students, Giger and Marsden, based on their experiment, proposed another model. Let us see that. Now the second model that was proposed about the atom, second prominent model, now before going for Rutherford's atomic model, we have to actually check with Rutherford's alpha ray scattering experiment. Okay. Now let me show you what this experiment is. So this in fact is a source of alpha particles. I mean, it contains a radioactive substance. Right? Now, see the alpha particles that are coming from the radioactive source. Were actually have to actually take let me just check. See the alpha particles that are coming from the radioactive substance are allowed to pass through this slit or the hole. Now this plate is made of lead. This is of course a lead plate. Okay. Let me put a gold foil. Let me just draw it on my own. It has to be this way. So this is the gold foil of a thickness almost 100 nanometers. Okay. Now, surrounding this gold foil see photographic plate is being placed. Okay. Now let us see what happens. This is the overall arrangement. Okay, this is the photographic plate. Okay. Now, consider the alpha particles coming from the radioactive substance. Now they are allowed to pass through the slit and of course are allowed to fall. I mean, of course, they fall on the gold foil, right? As and when they fall on the gold foil, just a right. You know, they were actually deflected. You know that the alpha particles are nothing but helium nuclei, nothing but positively charged. Okay. Now, even in the gold foil also, there is positive charge. Because of the repulsion between these two, you know, the alpha particles were deflected by different angles. Let me show you. Of course, very few of them went in straight lines. Oh, no. Without any deflection, they just went in. It has entered into the gold foil and it has gone in straight line. But most of them deflected by different angles. Let me also show them. Okay. So this way they were deflected. Even this way also. So that's how they were deflected by different angles. So based on this observation, he proposed some postulates. And there is something else to say. You know, this gold foil is actually coated by the fluorescent zinc sulfide screen. You have already come across this. Zinc sulfide screen earlier also. You know, as and when the alpha particles fall on the zinc sulfide screen, a kind of scintillation is produced. Okay. After that, of course, they get scattered. This is all the experiment, what they have done. Let us see what the postulates that were proposed based on this experiment. The postulates of Rutherford's atomic model. You know, based on the observations that were made, let us first go for the observation. Then based on the observations, we'll see what proposals were made. The observations were, most of the alpha particles went in straight line. Few alpha particles were deflected. Most of them went in straight line. Some, of course, were deflected. Most of them went in straight lines. That means they were undeflected, right? It is because, most of them went in straight lines undeflected because most of the atom is empty. Now, because most of the atom is empty, and of course, the nucleus is concentrated at the smallest portion, at the center of it, in a smallest portion. Let this be the atom. And this, of course, be the nucleus. Okay. Because the nucleus that has positive charge is concentrated in a smaller portion at the center of the nucleus. Let me tell you that the radius of atom is of the order of 10 power minus 8 centimeter or 10 power minus 10 meter. Whereas that of nucleus is about 10 power minus 13 centimeter or 10 power minus 15 meters. Comparing these two, we can say that atom is about 10 power of 5 times to that of nucleus. As far as the size is concerned, atom is about 1 lakh times to that of nucleus. So if you can consider the atom as a football ground, nucleus is just like a football. Just a basic comparison. So nucleus is located at the center of the atom within a small portion. That is the reason why, most of the alpha particles went through in straight line. This way, because there is no problem in going in straight line like this. Most of them went in straight line. Right. Few of them which went very close were, of course, deflected. Look at deflected. Like this. Yes, even this also gets deflected because it is going much closer. like this. See, the deflection is because alpha particles are positively charged. Even the nucleus is positively charged. Yes, of course. Rutherford proposed that there is a nucleus at the center of the atom, located in a small portion. And this nucleus is made up of, nucleus consists of protons and neutrons. These are collectively called nuclei. Okay. And suppose if, very few, of course, if suppose something goes this way, it is deflected back by larger angles, right? So this way, the deflection was observed. Next. So simple things can be given as the first one. Most of the atom is empty, right? That is the reason why the alpha particles went in straight lines. Otherwise, they would have deflected. But most of them went in straight line. Positive charge, of course, proton. In fact, the nucleus is concentrated in extremely small region. Yes, I told you the comparison also. Then about the nucleus. Nucleus consists of protons and the neutrons. Collectively called nucleon. Next. The most important thing is electrons revolve around the nucleus. Just as planets revolve around the sun. Interesting. Just as the planets revolve around the sun, electrons revolve around the nucleus. So this model is also called planetary model. In this, of course, the nucleus plays the role of the sun and the electrons are planets. In fact, it was told that there are electrostatic attractions between the positively charged protons present in the nucleus and the negatively charged electrons revolving around the nucleus. That is the reason why electrons are tightly held by the nucleus. They are held together. The electrons and the nucleus are held together because of this electrostatic attraction. Electrostatic attraction is the one that is generally operated between opposite charges. Okay. This is about Rutherford's atomic model, and these are These actually were the proposals or the postulates made by Rutherford. But there are certain drawbacks in this. Simply speaking, okay, let me just give you the drawbacks. It has two main disadvantages. The first one is fail to explain the stability of atom. What is that? You know, according to Maxwell's electromagnetic theory, Maxwell's electromagnetic theory, any revolving charged particle like electron any revolving charged particle like electron, while revolving, like suppose while revolving around the nucleus, should lose its energy continuously. It should lose its energy continuously while revolving and should actually spiral down into the nucleus. This is the problem. Any revolving particle generally loses energy while it is revolving around an object. In a similar way, when here also electron, while revolving around the nucleus, should lose its energy continuously and finally should spiral down into the nucleus. As a result, atoms should get collapsed. But this is not happening in the real sense. Atoms are stable. Electrons should spiral down into the nucleus. But this is not happening in the real sense. So there is something which is stopping the electrons from spiraling down into the nucleus. What is that? What is the logic behind this? Because if electrons really spiral down into the nucleus by losing energy continuously, then the atom should get collapsed. It is not happening in the real sense. So that is the first drawback. Rutherford failed to explain this. Rutherford failed to explain why electron is not spiraling down into the nucleus as per Maxwell. Then, you know, it actually failed to explain the spectra of atoms. I mean the spectra given by atoms. It is because it actually failed to explain the electronic arrangement. How are the electrons distributed? It failed in explaining this. Because it failed in explaining electronic arrangement, it also failed in explaining the spectra of atoms. Okay. So these are the drawbacks or demerits of Rutherford's atomic model. In order to overcome these defects or demerits, Niels Bohr proposed another atomic model called Bohr's atomic model. According to Bohr, electrons revolve around the nucleus. In a specified circular path. This is very important. Electrons revolve around the nucleus in specified circular paths having a fixed radius. Fixed radius. Now these paths are called orbits or shells. Okay. Now, see, every orbit is associated with a definite amount of energy. Now, because every orbit is associated with a definite amount of energy, the orbits or shells are also called energy levels. Right? As long as electrons revolve in these orbits, their energy remains constant. So this is the most important proposal made by Bohr, which of course Rutherford failed in explaining. He failed in explaining the point that electrons, why are they not losing energy and why are they not spiraling down into the nucleus? But according to Bohr, as long as electron revolves in a particular orbit, its energy remains constant. So this is very important. What is this? Energy remains constant. Means, it neither absorbs energy nor emits energy. Neither absorbs nor emits as long as it is revolving in a particular orbit. Okay. But you know, when they move from one orbit to another orbit, then of course they absorb and emit energy. Let us see when electronic transition occurs from higher energy level to lower energy level. Energy is emitted. From lower energy level to higher energy level. Energy is absorbed. Okay. Remember, as long as it revolves in a particular orbit, it neither emits nor absorbs. But during the electronic transition from one energy level to another, of course, energy is either emitted or absorbed. Now, the absorbed or emitted energy can be calculated using the formula delta E, nothing but E2 minus E1, that is equal to H nu, where E2 is the energy of higher energy level, E1 is the energy of lower energy level. Okay. Now, this is what is called a Bohr's frequency rule. Okay. Because here this nu is frequency. You can calculate frequency of the line formed during the transition. Let me just show you the same diagrammatical. Look at this. Okay. So that's how there is a force and nucleus as was proposed by Rutherford. Nucleus was discovered by Rutherford. Nucleus is positively charged. Of course, there are neutrons in the nucleus, but they are chargeless. Now the electron. You know, electrons revolve around the nucleus in specified circular paths of a fixed radius. Okay. These are the orbits Yes. Okay, let me just draw one more. Okay. Yeah, yeah. You have to just imagine, cannot draw it that perfectly. But the point that I would like to say here is, you know, I told you that as long as electrons revolve in a particular orbit, its energy remains constant. So that is the reason why, the orbits are shells or energy levels are called stationary orbits, stationary shells, or stationary energy levels. Because their energy is remaining constant. Now, these orbits, shells, or energy levels are represented by small n. Of course, later this small n was given the name principal quantum number. Again by Bohr himself. The stationary orbits, stationary shells or stationary energy levels are represented by small n. Let this be n is equal to 1. Look at this, what I have drawn here. Here the value of n is 1. And see, when n is equal to 1, it is called K shell. Similarly, take the second one. Now say for this n is equal to 2. Now when n is equal to 2, it is called L shell. Then go for the third one. For this n is equal to 3. So these are all principal quantum numbers. Of course, now we call them stationary orbits or stationary shells. But later they were named as principal quantum numbers. Now what is this? This is called M shell. Then go for this. Say for this n is equal to 4. And this is N shell. Similarly, when you consider n as 5, it is called O shell. Now that's how you will have infinite number of orbits in an atom. Of course, I have shown few. K, L, M, N, O, P, like that, it goes on. Okay, so this is how the electronic arrangement can be explained. See, supposing if you consider the electronic transition from, say, a higher energy level to a lower energy level. Now here, when electron is revolving, of course, it will have higher energy. And of course, the electron that is revolving in this orbit will have lower energy. So when an electronic excitation, de-excitation is occurring from this level to this level, in order to cope up with the energy of this level, it has to lose energy. It has to emit energy. Now, suppose if it is going from lower to higher, obviously to cope up with the energy of this, it has to absorb energy. So this is what I wanted to say. Now the absorbed or emitted energy can be calculated using Bohr's frequency rule. Okay. That is E2 minus E1 is equal to delta E, nothing but H nu. Next. One more interesting point. You know, the angular momentum MVR, where M is mass, V is velocity, and R is radius of the orbit in which it is revolving. Angular momentum of electron MVR angular momentum of electron revolving around the nucleus in a particular orbit must be equal to integral multiples of h by 2 pi. This was the proposal made by Bohr. The orbit in which the electron is revolving is n. N is of course an integer which takes up values 1, 2, 3, 4, and so on. Angular momentum of electron MVR, mass, velocity, and radius of the orbit, must be equal to integral multiples of h by 2 pi. This, of course, is called Bohr's quantum condition, because here n can take up integer values only, but n can never be in fraction. I mean, it cannot be like 1 by 2, 2 by 3, 3 by 4 like that. This is what is called Bohr's quantum condition. I mean, n takes up integral values only, but can never be in fraction. I mean, electron revolves in only those orbits in which its angular momentum is equal to integral multiples of this h by 2 pi, where h is of course Planck's constant, 2 and pi are constants again. Okay. So these are the postulates of Bohr's atomic model. Now coming to the defects or drawbacks of Bohr's atomic model. You know, Bohr's model could explain about the stability of atom, and it of course is an improvement over Rutherford's atomic model. Could explain stability of atom and the spectra of hydrogen and hydrogen-like species. What do you mean by hydrogen-like species? Nothing but those with one electron. Like for example, helium plus, Li plus 2, beryllium plus 3, etc. But failed to explain spectra of multi-electron species. I mean, those having more than one electron. Yes. Then next. See, it actually failed to explain Zeeman and Stark effect. What do you mean by Zeeman and Stark effect? Splitting of a spectral lines into still simpler lines or into fine lines in magnetic field is a Zeeman effect. The same splitting of spectral lines into fine lines in electric field is called Stark effect. Bohr's atomic model, in fact, failed to explain these two. Why are the spectral lines splitting into still simpler lines or fine lines? This was not explained by Bohr. Now coming to another drawback. You know, Bohr failed to explain about the fine spectrum of hydrogen. I mean, when the spectrum of hydrogen is recorded using a high resolution spectroscopy, it was found that every line is, in fact, a group of closely spaced lines. Every line is having a bunch of lines, bunch of closely spaced lines. And you know, these closely spaced lines are called fine lines, and such a spectrum is called fine spectrum of hydrogen. Bohr failed to explain this. I mean, failed to explain reasons for fine spectrum. Right. Then, you know, according to Bohr, angular momentum must be equal to integral multiples of h by 2 pi. But why? Why is angular momentum quantized? Why should n take up integral values only? Why can't it be in fraction? And the final one is, of course, Bohr failed to explain about the formation of chemical bonds. Okay. So these are the defects of Bohr's atomic model. Okay.